As promised, this is the Chapter 2.4 Real Zeros of Polynomials pre-calculus lesson that we didn't get to finish in class, so we're going to zip through it right now. You guys did the team challenge by factoring by grouping, and then you found the zeros. You didn't seem to have any trouble with that. We expanded on the real zeros of polynomials. You guys did this problem in class. You graphed it on Desmos. You estimated the roots, and then you guys did factoring. You factored it completely, and then you set each factor equal to 0 to find the roots. One root has a multiplicity of 3, and the other root has a multiplicity of 1. So there's your solution for number 1. Number 2, you were asked to determine if x minus 1 is a factor, and you do that through long division. You get a remainder of 0. So you do find that x minus 1 is a factor of px. Then you write it as a factor of the linear factor and the quadratic factor right here, but it's not factored completely. The quadratic factor can be factored to x minus 5x plus 2. So the complete factored version of p of x is written here in yellow, and then the solutions are here in blue. Remember, solutions are the same things as roots and zeros. So be sure that you guys factor your polynomials completely to earn full marks. Number 3 is the same thing. We were determining if x plus 2 is a factor. It was indeed through long division. We had a remainder of 0. We wrote p of x as a product of the linear factor and the cubic factor. We could factor the cubic by grouping, which you see here in the blue and the red. Then you get 3 factors, but this x squared minus 9 is a difference of squares, so that again can be factored. So the blue shows the complete factorization of p of x, and then the yellow shows the 4 solutions. Remember, the degree here is 4. That tells you the total number of solutions, whether they're real or complex. These happen to all be real. They certainly can be complex roots, and therefore they would be imaginary that you couldn't actually see, but there are roots. So really what you guys are doing here is what's known as the factor theorem. And this reads that the 2 examples, number 2 and 3 above, demonstrate the factor theorem. If a polynomial is a factor of a function, then it divides into it evenly without a remainder. You guys already know this. You worked on this several classes. You've been doing really great with the division. Or it has a remainder of 0. If you know the root, then you can also find the other factors using the factor theorem, or you could find the other roots. So we're going to go backwards. We're going to be, not go backwards, we're going to be given the root, and then you're going to write the factor. So in number 4, which I've worked through most of it, but you can pause it at any time and analyze a little bit more, they tell you the root. They tell you a solution right here. So the first thing you want to do is write the factor given the root. So you start it by setting the root equal to x. You move the 1/3 over, and then we get rid of the fraction by multiplying by the denominator. So 3x plus 1 equals 0, so therefore 3x plus 1 is a factor of px. So we took the root, negative 1/3, and we were able to figure out the factor of px. Number 2, I use long division to figure out the other factor, which happens to be a quadratic factor. So I divide 3x plus 1 into p of x, and I get x squared minus 5x plus 4. I didn't show the long division, but you can work through that on your own. Number 3, I write p of x as a product of the 2 factors I found, 3x plus 1, x squared minus 5x plus 4. But you always need to be sure to factor completely. And x squared minus 5x plus 4 can be factored to what you see in the blue, which is x minus 4, x minus 1. So the complete factorization of px is right here in yellow. Make sure you always write the complete factorization. And then the complete solution, all 3 solutions which happen to be real, are written right there. The degree is 3, so you can have up to 3 real solutions, but no matter what, you always have 3 solutions, whether they're complex or real. Now, let's say you're not given any root. You're not given any root, or you're not told any factor. You can use what's known as the rational zero theorem to find some possible roots. If no solutions or factors are given, one can use the rational zero theorem, also known as the rational root theorem, to create a list of possible rational zeros. Now remember, these are real. You're not going to find the imaginary solutions this way. This is just for the real solutions. Once this list is created, you can evaluate the function at each to determine if it is indeed a zero. This theorem only works if the coefficients of the polynomials are integers. That means no fractional no fractional coefficients of the polynomial. So you need to have all integers, which is what ours has been. So this is how you determine all the possible rational roots. You take the factors of the constant, which is the last term if it's written in standard form, and the factors of the leading coefficient, which is the coefficient of the first term if it's leading, and you divide them. The number of zeros, real or complex, is equal to the degree of the polynomial. Some of the zeros may repeat, hence their multiplicity is greater than 1, but you're still going to have that number of roots. In our next example, I'm going to show you how to find the possible zeros, then we're going to test them, and then we're going to be able to write the polynomial as a product of its factors. Here we go. Last example. Determine the possible real zeros of p of x. So you need to identify first the leading coefficient, which I've shown here in green, which is 1, and the constant, which I've shown here in blue. Test each one to find all rational zeros. Then write the function as a product of its factors. So we're not told any of the zeros. Obviously, if we graphed on Desmos, we could find them all. But this is assuming you can't use technology. So the first thing you're going to do is list the factors of the constant term. Those are the numbers that divide into 6. Plus and minus 1, divide into 6 evenly. Plus and minus 2, divide into 6. Plus and minus 3, divide into 6. Plus and minus 6. So these are all the factors of 6, the numbers that divide into 6 evenly. That's the first thing you do. Then you find the factors of the leading coefficient, which happen to be 1 in this case. There's only 2, plus and minus 1 are the only numbers that divide into 1. Then you list the possible roots. The possible roots are the factors of the constant terms, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, all divided by the possible factors of the leading coefficient. There could be so many combinations, but we are fortunate that we only have 8. So plus or minus 1 divided by plus or minus 1 is going to be plus or minus 1. Plus or minus 2 divided by plus or minus 1 is going to be plus or minus 2, etc. So what you see here in black are all the possible rational roots. So there are 8 possible rational roots. There could be so many more, which makes this very tedious, but this is how it could be done. So now you take each one of those roots, or possible roots, 1, -1, 2, etc., and you plug it into the actual function. So I'm going to evaluate the function p of x at p of 1. I substitute 1 in for wherever there is an x. Type that right-hand side into your calculator, or you could evaluate it by hand, and you would get 4. Well, we're looking for it to equal 0, so this is not a 0. It's not a root. Don't have to worry about 1. It's not a root. I do the same thing for -1. I plug it into the function. I evaluate, and I happen to get 0. That means that x equals -1 is a root. It is a solution to p of x. I repeat the process for p of 2. That happens to be 0 as well. So x equals 2 is also a root. I do the same thing for p of -2. I hope I didn't say p of -2 there. P of -2 winds up giving you -16. So it is not a root. X's -2 is not a root. I do that also for 3. P of 3 happens to be 0. So x equals 3 is also a root. I can stop here because I've already found 1, 2, 3 real roots, and the degree is 3. So that's the most number of roots I can have, period. So the roots of p of x are x is -1, x is 2, and x is 3. And now I can write it as a product of its factors. I move each one of those over to set those equal to 0, and then I can pick out the factors. So x plus 1, x minus 2, and x minus 3. If you wanted to multiply all of that out, you would get the function p of x, which you see at the top. But don't waste your time. So that's how you figure out the roots based on the polynomial using the leading coefficient and the constant. Your guys' homework is to do problem set 2.4.1. This is the last section before our exam. I wish you luck, and we'll talk next class. Hope this was helpful.